So, we discussed the previous, the next, and the opposite half edges in the half edge data structure, and that could help me in traversing. There is also a pointer to the face ref, which is the left face of an half edge, so that you can jump to the facets rather than jumping to the edges. Then the face has a reference to its any half edge, because a face has a number of half edges. It is okay for a face to have any half edge, because if you have access to one of the half edges, you can cycle through. You can jump to other half edges very easily. Similarly, for a vertex may have a valence of 6 or more or less. So any outgoing half edge is perfect. You have a pointer to that. You can always do one ring traversal to get to any half edge that you want. Okay, so half edge data structures are centrally built for ease of navigation. Is there any question on the half edge data structure before we move forward? Clear to everyone? All right. Okay, so that's my half edge data structure. The winged edge data structure is also similar. It's a bit bulkier than the half edge data structure, also a little bit older. So, and then half edge data structures can be optimized for triangles so that they occupy less space, but nevertheless you can have them for arbitrary polygons, not just triangles. Okay, so we discussed a lot about surface meshes. Let's see what are volume meshes. So similar to surface meshes, a surface mesh represents the boundary of a solid. What if I want to also model the interior of the solid? That is, I want to model the solid itself. I can do that with what are known as volume meshes. Again, it's a polygonal or polyhedral representation, right? It's no more, well, it's a polygon for 3D is a polyhedra, and we discussed a few polyhedra last time. Yesterday we talked about tetrahedrons and prisms and pyramids. Those are all some of the solids. So in a sense, for a volume mesh, I discretize the interior structure of a shape. For example, you can see here a tetrahedral mesh of this space, and you can see that there are a lot of tetrahedrons inside. And then similarly, you can also have a hexahedral mesh, which is composed of hexahedrons. So what is a hexahedron? Anybody?
A cube.
A hexahedron is it's a well, not necessarily, well, not a cube is a hexahedron, but a hexahedron is more general. So it could be anything that has 6 faces. Hex means 6, hedron means face. So anything with 6 faces is a hexahedron. But yes, a cube is a hexahedron. But the other way around may not be true. So tetrahedron, hexahedron. So you fill up the entire interior with these elements, and that becomes a volumetric mesh. So that's about surface and volume meshes. And by the way, there are similar data structures. You can extend these data structures for volumetric meshes as well. Okay, so now you have a surface mesh defined. Maybe after I cover the subdivision surfaces, I'll give a short break to the participants. Now, let's say we have a mesh defined, and it's a very coarse mesh. What can I do to smooth it out? What can I do to improve its appearance? And it seems like there is a number of ways for you to smooth out. The foremost thing that comes to my mind is look, my mesh has a very low polygon count. For example, in this car example, it's the first one is a very low poly. This one is a very low, is a low poly mesh. So one thing I can do is increase the number of polygons and hope to have a smoother appearance here, and this is known as subdivision of a surface. So what is subdivision? Subdivision is of a surface is repeated refinement of a coarse mesh, otherwise also known as a control mesh. And in the limit, that is, if you keep on subdividing the facets, you get a smooth surface, or you could also figure out mathematically that it sometimes would result in a, well, not sometimes, actually you can prove that different types of algorithms will result in different types of smooth parametric surfaces. So Bezier and splines. The new vertices in a subdivision surface are calculated by taking convex combinations of fold points. For example, there are certain schemes when it comes to subdivision of meshes. If it's a tri-mesh or a triangle mesh, you could subdivide every triangle into 4 new triangles by splitting the 3 edges of a triangle, like as it is shown in the right figure at the top here. Is that you could insert new vertices on the edges and split the triangle. If it's a quad mesh, you could do a quadrilateral subdivision. That is, you insert a vertex in the center of a quad and on all the edges and connect them. So a quad is then split into 4 quads. Now, you can always convert any mesh, as in any polygonal mesh, into a quad mesh by inserting a point at the center. So does anybody know how that works? Very quickly, I will again draw and tell you how to do that. And we'll come back to this one.
Sir, while you are switching, I had one more quick question. What is like non-convex way of combination of the like non-convex method? So you have mentioned that by like convex combination, we sort of get a we can like refine it in order to get it like get the coarse mesh smoother. So like
so
what is
non-convex combination can result you in undesired vertices. What do you mean by what is non-convex? Convex, do you understand what is convex and non-convex combination?
In this context, I'm not able to figure out. But
no,
in
so
general,
the context is the same. It's the linear algebra context. Vignesh. Convex combination, non-convex combination. It's the same idea. There is nothing mesh specific here. So like you take convex combination of vectors, numbers, it's the same idea.
Okay.
Right? It's the same idea. We usually don't take non-convex combinations because that can result in artifacts. So you usually take convex combinations. It's the same idea as it is in linear algebra.
So it is like we are just taking care that the subdivisions are also remaining convex. That is the only context here.
Yes, you could say that there could be a consequence. That could be one consequence of that. Yeah. Okay. Anyway, so where were we? Yes. So if you have a triangle mesh, so facet split. Well, let me not call it facet split. If I have a triangle here, how could I subdivide it to make it a quad? I could insert a point in the center and then on the facet and join them, and it becomes 3 quads rather than 3 triangles. And in general, if I have a polygon, let's say a hexagon here, I can always do the same and create a quad mesh out of a polygon mesh. This could be handy if you have a polygon mesh and you wanted a quad mesh out of it. Right, so it becomes a general recipe to create a quad mesh. Then, of course, the quad mesh quality you need to take care of, because that may not be a great quality quad mesh, but yeah, you can always define it and do it. But if it's a triangle mesh and you want a triangle mesh, you just subdivide the edges and split it into 4 triangles like this. So that's one. And in the limit, these eventually boil down to some Bezier patches or spline surfaces. So right, so there are different types of vertices in a subdivision. You would notice that there are vertices that are shared by coarse. There is a spelling mistake here. C-O-A-R-S-E. I'll fix that. So vertices shared by coarse and refined mesh. Then there are edge vertices, that is the ones that you inserted on the edge. And then there are face vertices, which I just explained to you. Usually a subdivision scheme, you could define a subdivision scheme using matrices, but it's quite handy to specify the subdivision scheme by a mask. And there are usually two types of masks that are specified. One mask is that specifies how a new vertex is computed from old ones. For example, if you see in that figure, the first figure, this dot in the center is a new vertex created on an edge. And these numbers 1 by 8, 3 by 8, 3 by 8, and 1 by 8 tell you the weights of the original triangle mesh, weights of the adjacent triangles of this edge for the vertices. So you multiply the vertices by these weights and take a convex combination, and that becomes the new coordinate for this central vertex, right? So that's how you create a new edge. And this one is the mask for the loop subdivision scheme, which we will see in a moment. So that's for the new vertex. Then you need, and if there is a face vertex that is inserted, you will have a mask for a face vertex. So this mask is nothing but a configuration and weights for the old vertices that will be combined to generate a new vertex, which could be a new edge vertex or a new face vertex. So that's one mask. The other type of mask is how to update the old vertices. The old vertices of the mesh also need to be updated, because a subdivision will change the appearance of the mesh. There are two types of subdivision schemes, the ones that are approximating schemes and the ones that are interpolating schemes. The approximating schemes will change the overall surface. So not only the new vertices are created, the old ones are also modified. The interpolating schemes will not update the old vertices. So the second type of mask will not be present for the interpolating subdivision schemes. Loop is a approximating subdivision scheme. So we have a mask for updating the old vertices. So in this case, if you look at the right figure over here, you have the one ring around a vertex that has to be updated in the old mesh, and you have this the V here in 1 minus V beta is the valence of the vertex, and beta is a weight that has to be calculated. There's an expression for that, formula for that. We'll look at that in a moment. But I hope you understand that there are two different types of masks. one for creating new vertices and one for updating old vertices. And then you have to keep, if you keep doing it for all triangles iteratively, you'll get versions of refined meshes as you go down the iterations. Okay, so the masks are clear. Then we can discuss some of these schemes and look at their masks. Okay, so let's take a look at the loop subdivision. The loop subdivision scheme is a very well-known scheme. It's a triangle-based approximating scheme. So the surface gets shrunken, as you can see in this example down. We started with a single tetrahedron and created more tetrahedrons. Created more triangles on the way. So a tetrahedron has 4 triangles. So we started with 4 triangles initially, and then every triangle was split into 4 more triangles. And so 4, 16, and then 64, and so on and so forth. There's no limit. You can just keep going. So again, new vertices are created only on edges, and the limit surface is C2 for regular regions. For regular vertices, it's C2, and it has been proved that it's C1 for irregular. If there are vertices that don't have valence of 6, then it can result in a C1 region around that vertex. And those are the masks for loop subdivision. And for updating the old vertices, you have to calculate this beta weight, which is given by this expression 1 over v 5 by 8 minus this term that depends on the valence again. So v is the valence of a vertex, right? So this is loop subdivision. And a consequence of loop subdivision is that the shape of the object decreases. Of course, eventually it sort of, stabilizes at a point, but initially there is a shrinkage, observed shrinkage. Then there is another well-known subdivision scheme called Catmull Clark subdivision scheme. This is again a quad-based approximating scheme. So we are not working on triangle meshes, but on quad meshes. And new vertices are created on edges. So there is an edge mask, and also on the faces. So there is a face mask as well. And the weights are as shown here. And again, the limit surface is C2 and C2 for regular and C1 for irregular regions. Then you also have to update the old vertices, and the mask for updating old vertices is given in terms of the valence of the vertex in question. Right. So that's my Catmull Clark subdivision, and that's how Catmull Clark surface look like. So you can see that starting from a very coarse mesh, you eventually get a very fine mesh, and it also looks very smooth because in the limit it is some very smooth parametric surface in the limit. Then I've also included here one interpolating scheme known as the modified butterfly scheme, and it's a triangle-based interpolating scheme. So in a sense, the overall shape of the object, the shape of course has to change a little bit because I'm adding more vertices, but the original vertices do not change. They stay where they are. And right, so there are triangles are split in a 1 to 4 fashion. That is, one triangle is split into 4 triangles, similar to the loop subdivision scheme, or as a matter of fact, any triangle being split by edges. And there is no vertex update rule since it's an interpolating scheme. So the old vertices stay where they are, and that's why it's an interpolating scheme. Only the new vertices are created. And right, so there are these 2 face rules here, and the one on the left does a new vertex creation, and then that is to be updated with another face mask here. The two face masks here for updates. And these are these expressions for calculating. So the difference approximating versus a interpolating is that in interpolating subdivision scheme, there is no update of older vertices, only the newer vertices are created. Okay, so that's modified butterfly scheme. And okay, so as I promised, let's take a short break now. It's 10:30, almost 10:30 now, 10:33 to be precise, my machine, and we have this session until noon. So this probably could be a good time to take a short break and then come back. So let's take a break. So Aditya, how long should the break be? Is it 5 minutes okay, or 10 minutes?
Yes, 5 minutes should be fine. So we can start at 10.
5. Yes, let's come back at 10:40. Okay, so any quick questions before we start with the lunar triangulation? Okay, so let's now discuss about the lunar triangulation. And so given a set of points in let's say let's do it with 2D. So given a set of points in a 2D plane, I can triangulate. There are many ways in which I can triangulate. A lunar triangulation is a special type of triangulation. That is, it's a special way of tiling, connecting the points in a plane. It's a special way to do that. And what is special about it is, and I'll tell you first before reading the sort of the formal definition, is you have this. Okay, you don't see my cursor. You do. Yeah, it moves. So let's say you have these points in that left diagram. You have these points in the plane, and you want to triangulate them. So if you are not doing Delaunay, you can connect them in any fashion, but that may or may not give you a good looking triangulation. What Delaunay does is that it connects these triangles in such a fashion that it minimizes it maximizes the minimum angle, I believe. But for every triangle in that Delaunay triangulation, the circumcircle of that triangle does not contain any of the sides. So these points are known as sites. A circumcircle of every triangle in Delaunay triangulation does not contain any fourth point of the site. And that's Delaunay triangulation. There are algorithms to construct Delaunay triangulation. So given a set of sites P, let's say these points, belong to the set P. A Delaunay triangulation is a simplicial complex. Now there is this new word coming, simplicial complex. So what is a simplicial complex? Anybody knows what is a simplex? Simplicial complex in this case implies the simplest three-dimensional, a simplest d-dimensional entity, a primitive that is possible in that space. So for 3D, a simplex is tetrahedron. You don't have a simpler object than a tetrahedron in 3D. In 2D, a simplex is a triangle, and in 1D, what would be a simplex? A line segment. Okay, so a Delaunay triangulation, it's a simplicial complex. A simplicial complex is a collection of simplices connected together. So it's a simplicial complex such that k plus 1 points in P form a Delaunay simplex of their Voronoi cells that have non-empty intersection. Maybe this definition makes more sense once we look at the Voronoi diagram. So come back to this once. For now, maybe let's ignore this because we haven't looked at the Voronoi diagrams. I think I did a change of slides, so I had Delaunay after Voronoi, and then I realized that Delaunay should come first. So I just moved the slides, but I didn't update the sort of this definition. But we'll come back to this. But Delaunay triangulation, the main idea with Delaunay triangulation is that the circumcircle of every triangle of a Delaunay triangulation contains no points of P in its interior. That's a very peculiar property of a Delaunay triangulation, and this is known as the empty circle criterion. That is, the circle is empty of any fourth point in from the set of points P. On the right, you can see a typical Delaunay triangulation, and usually Delaunay triangulations look great if your point distribution is random but not skewed. Then you see a near uniform triangulation compared to any other triangulation that you may devise. Delaunay triangulations are usually good because it can be thought about in terms of some optimization. So then you need a test. So whenever you want to create a Delaunay triangulation, you need this predicate in circle that takes 4 points and decides whether the point P4 lies inside the circumcircle of points P1, P2, P3 or outside that circumcircle. Right? So this test in circle P1, P2, P3, P4 will help you there. And it's a very simple test. You have this matrix. You calculate the determinant of this matrix, and that works great. So for those who are wondering why this matrix works, I can maybe very quickly explain you what's the deal with this matrix. Graphically, I can show you why this works. All right. So let's consider that you have, that's my plane on which I have these 3 points, and these 3 points always define a circle, right? I need exactly 3 points to define a circle. If you had noticed, that matrix had some quadratic terms, and remember, this is the x, this is the y. So every coordinate has xy coordinates, right? So let's say that is my origin. What I do is that I lift these points in 3D by a parabola. So I have this parabola, z equals to x square plus y square. I lift every point into the third dimension with this parabola, and by the way, this parabola does pass through the origin. So I'm trying to draw it as best as I can, but pardon my drawing, it may not be great. Try to well, it's not a parabola, it's a paraboloid. It's in 3D, right? So you have a paraboloid like this, and when you lift these points, each of these points will go to its place on this paraboloid. Let's say that's the lift of these points, of these 3 points on the paraboloid, and let's say that was the triangle that these 3 points will form. So in 3D, this triangle will also get lifted, and this will define a plane in 3D, right? So I'm gonna draw this 3D triangle, lifted 3D triangle, and this is going to define a plane. I hope this yellow line is visible. Otherwise, let me also make it greener. That might be better for visibility. Let's say that's my plane. That's the lifted plane. So come a third point over here, and I lift that as well onto this paraboloid. So these 4 points in 3D space form a tetrahedron. Okay, these form a tetrahedron, and there is this lifted plane pi. So depending on either the fourth point was outside or inside, the volume of the tetrahedron would be negative or positive. That is to say, it's a signed volume, so it would either be positive or negative, and it would be negative. So volume, again in black. So volume negative if, let's call it P4, is P4 outside, and volume positive is P4 inside. And graphically, you can see that if P4 is outside the circumcircle, then it's going to be a negative volume. And I can also draw the inside case when, you know, I haven't drawn this circle here. The circumcircle would be something like this. It becomes the diagram becomes a bit crowded, but I hope you can understand. So if this point is inside and you know, we lift it, then it becomes a tetrahedron that is pointing down. So it has a positive volume. So that's the idea behind this in-circle test. Is it fine by everyone? That's the graphical, you know, intuition behind that test.